Hey there, folks. It's Professor G. How you doing today? I want to take a little time here and talk about this long-lost PowerPoint. This is something that I knew I'd created, and whenever I would give the oceanography lecture, in the back of my mind, I'm like, dang it, I know there's a slide about this. Where's the slide about? And what I think is this is really probably the first oceans lecture I wrote. And then that intro to oceanography came later, perhaps because I couldn't find this one or I wanted to make it more complete. But I inadvertently ended up leaving a few things out. A few more than a few things, actually. So in future semesters, this is likely going to be these two lectures might be blended together. But for right now, I'm just going to present this one as it stands because there's some helpful stuff in here. And when we do come to stuff that is redundant, we'll just sort of glaze over it or gloss over it. All right, so this is definitely a companion to, an addendum to the intro to oceanography lecture. And I'm not sure that this chapter number is even still correct. Probably several editions later of your textbook. So you've heard me say a couple times, more than likely, already, that the Earth is nearly 3/4 water, right? So we're looking at approximately 71%. And I know these numbers are too big to really hit home, but you know, that 140 million is awfully close to 197 million. And it's just sort of reiterating the idea here that, again, nearly 3/4, okay, is covered. That's a lot of water. As you probably know, it's a whole lot of water, but because it is salty, it's not exactly usable directly. And when we say usable, of course, we mean, can you drink it? Of course, we use the oceans for so much, and they're responsible for so much. That's sort of the point of this whole unit. But when people say usable water, they mean fresh, usable, i.e. drinkable water. This is kind of neat. Never thought about it, maybe. If you've ever looked at a map, the continents are kind of off-center a little bit. We're more focused on the northern hemisphere. So 40% of the northern hemisphere is land, where in the southern hemisphere, only a little under 20% there is land. I'm not sure if this goes right into a map or not. I forget. Yeah, it does, but I put it sideways so you can see it better. But it really still accentuates the point here. You've got Africa, South America, in the South Pole, and Australia, right? But look at this. I mean, this is, I think, really what sort of offsets it, is this whole hunk of Eurasia, as we call it. That's a lot of land. A lot of land. Did I forget Antarctica? Good gracious, I forgot Antarctica. And certainly at the South Pole we have Antarctica, but still, almost, what was it, double? Yeah, in the double the land in the northern hemisphere. So hopefully you knew this, but just wanted to take a couple moments and remind you. And this also ties into one of our part of our lab. We've got 4 oceans. All right. I'm sorry, I have a very whiny cat in the background. I'm not sure if you could hear it. It is begging to go outside. And I don't want it to go outside right now. Go lay down. Shh. Sorry. So we've got the Pacific Ocean, the Atlantic Ocean, the Indian Ocean, and the Arctic Ocean are our four main oceans. Of course, there's this sea and that sea, and even a few that use the word ocean again. But these are the four big ones. The Pacific will give you a North American-centric sort of view of things, okay? The Pacific Ocean is to our west coast and goes all the way over to the east coast of Asia. And the Atlantic Ocean, of course, is on the east coast of North America and goes all the way over to the west coast of Europe. The Indian Ocean is over to the east of Africa and south of Asia. And the Arctic Ocean is, there you go. All right. That's what we call the ocean to the north. I don't know why I didn't mention the word Southern Ocean. I don't, you just really don't come across that too often. But I wasn't going to white it out on here, Sorry about that. I gave in and let the cat out. So anyhow, you four main oceans, 5 if you count the southern. A little more in-depth look. Pacific Ocean is the largest ocean. That sounds like a really great multiple choice question, doesn't it? Which of the oceans is the largest? Greater than half of the total surface area of all the oceans. This is a really cool factoid. All of the continents could fit into the area that contains the Pacific Ocean. Pretty crazy. And it's also, anecdotally, the deepest ocean. Next, we have the Atlantic Ocean. All right, and the Atlantic Ocean is half the size of the Pacific. It's not as deep, and it's also fairly narrow. The Indian Ocean, even smaller. There's no dashed lines that separate these things. Oftentimes, there may be a pesky continent in the way, but the Indian Ocean, and in particular, just to go back real quick here, all right, so there's a few things here, but it more or less blends into the area that's the Pacific. Again, there's no dashed line. The Arctic Ocean, okay, is the smallest and the shallowest. All right, here's where you're going to see some overlap, at least one of the first examples of overlap with the oceanography. Some of this property stuff did carry over. So we have salinity, temperature, and density. If you wanted to, say, study the ocean water, these are 3 aspects that you would look at, okay? The big thing we like to remind you, I probably called it salt water already myself, okay? It's not just salt as you know it, table salt, sodium chloride. There's a whole lot of other stuff in there. Chemically speaking, if you've had a chemistry class, you might know what it means to be a salt, okay? It's sort of a category of compounds. We're not going to concern ourselves with that in here, but it is a general term for something in chemically speaking. Okay, so there are other salts out there. So about 3.5% of the weight, the mass of a gallon of water, let's say, if it were ocean water, would be dissolved solids. So in other words, not just hydrogens and oxygens, what makes up water, okay, but water plus some stuff. And that's what we talk about as the salinity here, the total amount of dissolved material in water. I don't think it's in this lecture, but one of the great examples I really like is that water bottle picture you probably saw in the other lecture that shows the different amounts of salinity by the various water types. Anyhow, the average salinity of seawater, as we just talked about up here, you see down here, is 3.5%. So what else is salt? Well, there's the sodium chloride that you know. There's magnesium chloride, something called sodium sulfate, calcium chloride, potassium chloride, and a handful of others. These are just kind of like the big five. Okay, and there's 5 more, but we're not going to bother you with those. Unless they show up here. So this is just an example of showing you what that 3.5% looks like, okay? In case you were having trouble. And this is a blow up of everything that's in here. So where did all that stuff come from? Well, mainly from weathering and erosion, which is the breakdown and transportation of rock material or material at the surface of the earth. Okay, as rocks break down. For example, you might be familiar with sometimes how lakes can have algal blooms, right? If you live around here, everyone loves to go to Sylvan Beach, and sometimes they just have to close because the algae bloomed, and you might, maybe you know why, maybe you don't. What happens is a lot of the fertilizers on the remaining, the surrounding farm fields can wash in after heavy rain, for example, wash into the lake. And not only is that food for, say, corn and wheat or whatever you happen to be growing, but it's also food for algae. So in a similar way, at any rate, the rocks and minerals and elements and whatnot that break down at the surface of the earth can wash away and end up into the oceans. Also, there's the process of outgassing. Okay, outgassing talks about when a volcano erupts, all that thick billowing smoke that you see coming out of a volcano is actually water vapor with a handful of things dissolved in it. Okay, so there is that, and there's actually one other thing that didn't make it to this cut. Yeah, I don't see it on the next slide here, and that is sort of a major original event. Okay. And sort of an ongoing, to a lesser extent, event, and that is the addition of materials from comets. Okay, comets you may know of as dirty snowballs, and while they are by no means the primary source of the Earth's water, they certainly contributed to the Earth's water, and as they came into our atmosphere and melted away, they contributed some material to the oceans as well. So this is kind of neat. If this is an ongoing process, why doesn't it keep getting stronger, right? Well, it's some chemistry and kind of a cool little balance that life has going on in the oceans. All right, those are actually many of those ingredients are actually providing nutrients, for lack of a better word, for the organisms that live in the water. So they are taken up, absorbed into the bodies of the animals, into the material of the plants and algae and so on and so forth. And also, Water can only hold so much of a certain thing. Think about when you were trying to make a Kool-Aid or hot chocolate. You could only dissolve so much of that in a couple tablespoons, okay, for example, into your glass. Believe me, as I always say, we talk about this in Sedimentary Rocks lecture that you guys didn't get. But there's if Swiss Miss or Kool-Aid could get you to dissolve, half a cup of Kool-Aid into a glass of water, well, they certainly would, right? They'd sell more Kool-Aid that way. But simple fact of the matter is you can only dissolve, we'll just say 2 tablespoons into 8 ounces of water, or whatever the formula is on the back of the container, right? It can only hold so much. So what happens then is you approach these, solubility is the word they use, those levels, saturation, right? It forms deposits. So again, something we don't necessarily want to get into at this point, but the water can only hold so much stuff. So what happens is we end up getting deposits, and that's where we get our rocks. And once those are uplifted out of the oceans through a handful of other processes, of course, they could break back down, get transported back in. It's a wonderful little cycle there. All right, what is this slide about? Average salinity, ? Again, this PowerPoint has been lost for years, so some of these catch me by surprise. Okay, so, and we do talk about this with the different types of mainly near shore environments. You heard the word estuary in the other lecture. You will hear it. And you might also hear about some of these really brackish waters, extremely salty areas. What this slide is telling you is it's not so much that we ever change the amount of dissolved solids. It's that we can change the amount of water, right? You could add fresh water by being near a coast, and a stream or a river would empty in, and that would dilute it, so to speak. Or if you wanted to try and up the concentration a little bit, you've all heard of, like, say, the Dead Sea, right, which is really, really salty, or Salt Lake in Nevada. I'm sorry, Utah. In Utah, the water evaporates away. The output exceeds the input, so to speak, and it concentrates the salts. So that's why it's an average. There are areas where the water has a lower salinity, and there are areas where the water has a higher salinity. All right, so that was the first. Remember, we're talking about 3 factors that we look at when we're assessing ocean water. Salinity was the first. So temperature and density, okay? For the most part, temperature changes with depth. Okay, the water is going to be warmer near the surface, generally speaking, and colder as you go deeper. Also, density increases as temperature decreases. All right. Cold water is more dense than warm water. The sun warms the surface waters. And as you probably could have guessed, water in the tropics is warmer than water towards the poles. The tropics receive more sun. You probably recall the lecture we had about the sun's energy coming into the Earth and how it warms different areas more so than others. Also, we've got something called a thermocline. And don't worry too much about this, but it talks about the therm, heat, right? it talks about how the temperature decreases, or in some cases, depends which way you're going, increases the change in temperature, I guess would be the easiest way to say it, as you go through the water. Isothermal, iso means equal. Remember your isosceles triangle. It's just all cold when you get, to a certain point. And water, of course, can only get so cold before it freezes. Salt changes that number. Okay, so salt water can get a good bit colder, but I don't know that we need to worry about this too much either. D equals m over v, of course. Mass per volume is density. So we could affect the mass a couple ways. We already talked about temperature, right? We said increasing temperature decreases density. I think actually we said it the opposite a moment ago. The colder water is more dense, is what we said. It's the same thing, two sides of the same coin. Do not worry about pycnocline, please. And it's important, if you're an oceanographer, but right now we don't need to worry about it. But also, if you think about it, we were just talking about dissolved solids with salinity, right? Certainly, if you could dissolve more stuff into that water, it will change you'll make it more dense. And also, again, I think I said this in the other lecture, this isn't just a chapter in a book or two chapters in a book. You could take this class for an entire semester. Hell, I mean, there's oceanographers out there. They took this, as their college degree or up to a master's or a doctorate. So we're just giving you an introduction here. So much stuff is being glazed over. But certainly as you change the temperature of the water, you can get more stuff into it as well. So it's fairly complicated. Keeping it simple. All right. Do not worry about this, at least for testing purposes. If you think it's cool, feel free. But not going to make the cut for when I combine these lectures at some point. So we already addressed the first bullet here. We said it's pretty much just cold all the way through. But the second one here is becoming fairly important recently. If you pay any attention to the climate change and the ice caps melting conversation. At first, they were primarily concerned with the simple fact that we were just adding more and more liquid water to the situation, right? And they were busy doing the calculations for that. Well, it took them a while to process, so to speak, the idea that this water coming in is very cold water, and despite the fact that there's little temperature change there, this cold water comes in and it sinks right down, and it displaces some of the water that's down deep, and that again has some compounding effects. So they you might hear about it again if you pay attention to that kind of stuff. It is a new variable, so to speak, in the conversation. And again, you have fresh water coming in, mixing with the salt water plus the temperature differences. It's more than just we're adding to the volume. So it's kind of neat, and of course, rather complicated. This is nothing too horribly important again for our purposes. Okay, I definitely know this is in the other conversation, but just a reminder, the HMS Challenger was the first sort of official oceanographic, there we go, endeavor that we took. And it did a heck of a big job. Bathymetry, remember, is the sort of the topography of the ocean floor. Topography is the lay of the land. Like if you were at the surface, you'd be talking about whether there's valleys or mountains or whatever, plains. Okay, so that's this same word, but applied to the same idea, but applied to the ocean floor. They use bathymetry, and also depths are implied therein. Obviously, if you have a mountain, it's going to be closer to the surface of the ocean than if you have a giant trench. Okay, that's what we call a valley in the ocean. Bathos and metry, a little Latin English for you there. Could you imagine, we've got all this cool machinery nowadays. They did it with a rock on a rope. Yeah, they probably had metal, but still. A fathom, this is really neat. This may or may not be in the other lecture. It's 1 arm's length of rope. Okay, so when they said, something was 1,000 fathoms, that's some guy sitting there stretching out. Okay, 1 length of rope, 2 lengths of rope. All right, imagine this rope running through and you spreading your arms out to either side. That's about 6 feet. Feel free to check. That's it's just what they tell us, but I suppose it varies with the individual. But at any rate, doing that 1,000 times, right, to try and measure the depth of an ocean. That's 6,000 feet. I mean, that's some pretty deep water, but there's a lot of deep water out there. And this one here, you certainly wouldn't be measuring with rope, right? You got 5,280 feet to a mile, right? You're looking at almost 7 miles. Well, here it's actually translated already right there, calculated. But yikes, that's a lot of rope. They probably ran out of rope before they hit that one. Thank goodness. Sonar. All right. Echolocation, you may have heard of that as well. Bats and dolphins use a very similar system. They still use it with cell phones, right? When you ping a tower, that's how they try and locate, lost hikers and whatnot, or fugitives. They can ping your phone and tell by how long it takes to come back to the cell tower, roughly how far away you are from it. And of course, you use 3 points, call it triangulation, right? They can narrow you down pretty quickly and find you and rescue you if you're lost, or throw you in jail if you're a bad guy. But we use very similar ideas when we're underwater, okay? The sound travels differently through water than it does through air, but it is the same idea. See right here, speed of sound in water. That's different. And then there's some more stuff going on. It's always with the math, isn't it? Bathymetry. It's called bathymetry for the pronunciation impaired out there. Satellite altimetry. All right. We could do it from the air now. You don't even have to cruise around with boats. All right, continental margins, ocean basins, oceanic ridges, that all comes up in the other PowerPoint. Just cruise through here real quick. So the continental margins, all right, continental crust meets oceanic crust. They are 2 different types of rock. All right, this isn't my geology class, so we won't assume that you guys know granite and basalt, but They're both igneous rocks, which means they both formed out of magma or lava. Okay. And the ocean is a different type of rock than the continents are. So we have two types of continental margins, active versus passive. You could probably guess what that means. An active margin, you're basically at a plate boundary, okay? And since we're talking about continental margins, we really only have this subduction zone here. And depending on the semester, depending on how long it takes me to re-record this, you may or may not have had plate tectonics conversation already. This semester, we have had plate tectonics already, so you know what a subduction zone is. But basically speaking, just as a reminder, at a subduction zone, oceanic crust and continental crust are coming together underwater, and the oceanic crust loses the battle. It gets pushed down into the mantle and melted. All right. But the other type of margin is a passive margin, and there's not a plate boundary there. So I'm not sure why I didn't give examples. It looks like I might. Let's just real quick just tell you here. So a North American example, West Coast is an active margin. Okay, you have the Pacific Ocean is on its own plate called the Pacific Plate. North America is on its own plate called, well, guess what? The North American Plate. So right there, where the Pacific and the North American meet is a plate boundary or an active margin. Well, the North American Plate goes literally to the middle of the Atlantic Ocean, where it joins the Eurasian Plate, right? So at our east coast, we don't have a plate boundary there. So that would be a passive margin. Okay, so passive margin, wide sediment-covered areas where continents are firmly connected to the ocean floor. And where we see these, we see, again, three more familiar terms: continental shelf, continental slope, and continental rise. This is all covered in the other lecture. Oh, just a reminder, before I do gloss over this, don't mean to harp on the whole sea level change and climate change and whatnot, but hey, it is in our science class. It's carved with river valleys, the continental shelf, right? This is, imagine yourself at the beach and you're walking out in the water, and it gets really, really deep, and then it gets really, really deeper. Well, the shelf goes out farther than that. You couldn't stand with your head above the water still. If you ever took a fishing expedition out, more than likely you were still over the shelf. You got to go a long ways. Okay. Anywho, a lot of that was exposed during the ice ages when all of the water, well, not all of the water, a lot of water was taken up into the glaciers. There's only so much water, right? Remember the water cycle. We looked at almost a 300-foot drop. It varied place to place, but 300-foot drop in sea level. And that doesn't mean that it's just 300 feet out farther than where the beach currently is. It's talking about depth, elevation change. And you could go oftentimes a good bit farther than 300 feet out horizontally before you find a change of 300 foot of depth, right? So at any rate, this point being, we find animal fossils, plant fossils, okay, as evidence. We find, it takes all of an hour watching the Discovery Channel or National Geographic or the Nature Channel, whatever you happen to watch, to see some of these submerged cities, okay, that are off the coast now, and they're completely under, water, 50, 100 feet of water. They didn't build those underwater, right? They built them on land. So this is why so many of us are just shake our heads when these people argue that, sea level change isn't a thing. Of course it is. Of course it is. What they're really arguing over is that they don't want to say that we're responsible for it. And, we are contributing to a natural cycle. Sea level is going to come and go. It has many times without us monkeying about, okay? But we are accelerating it is the problem. So we are not 100% the cause, but we are definitely speeding things up. Anywho, moving along. Continental slope, okay, between the shelf and the rise. And this is where that boundary between the two crusts occurs. And then the continental rise. And this one always bothered me as a student. Maybe you guys figured it out a long time ago. I'm just a dodo. But I'm thinking of it as, again, walking out from the beach, right? And you're going downhill. So why the heck do they call it a continental rise? Well, of course, it's from the other direction. Remember, the majority of the planet is ocean. So you're coming in from the ocean. So you're rising up to the continents. You dig? Okay. So it's a rise from that angle, from that perspective, from that direction. And you've seen this picture. So, active margins, jumping over to the west coast, North America. We talked about this already. There's other places, of course, not just the west coast of North America. Here's what happens. And going back to our conversation about volcanoes, remember that chapter? This is a great way to get volcanoes. It puts a lot of extra rock material rather close to the surface, mixing it in with water that's coming down in this little this zone here where everything's getting mixed up. And that makes it really, really volatile. Throws all kind of extra gas in there, and that just makes it really want to bubble up and break back through. All right, now we're out into the basin of the oceans. This is, for all intents and purposes, the ocean floor. And it has, just as much, if not more, diversity as we see on land, we see out there in the oceans. Okay, it is just an amazing landscape. So I mentioned already, trenches are kind of what we would call valleys out there. They are sites where plates are coming together. Okay. We do have plains. They call them the abyssal plains. This is where our word abysmal comes from. Seamounts are underwater volcanoes. 1 million of them across the ocean floor. Can you believe that? Sometimes they come to the surface and become islands. Mostly they don't. We don't have 1 million islands out there. For way too long, I pronounced that Guyot, right? How else would you see it? It's Geo. And these were things that previously broke through to the surface but wore back down. Okay. And they're kind of just these more or less flat-topped, kind of like mesas, if you know what a mesa is, right? So underwater mesas. Ridges are mountains. The Mid-Atlantic Ridge is a really popular one. It's a giant mountain chain. Essentially runs from, down the middle of the mid-Atlantic. But it's the longest and tallest mountain chain in the world. I almost said it runs from the North Pole to the South Pole. Not quite, but it's big. Big, big, big. A divergent plate boundary means it's pulling apart. So what's happening is that the ocean floor is cracking open and new material is coming out. Lava is coming out at the surface, and it's building up this mountain continually. And again, every so often it breaks the surface of the earth and we get an island. All right, so 40 minutes. That's not too bad. Like I said, I just wanted to add some of this stuff that, in my mind, has been missing from our lecture for a very, very long time. So thank you for listening. Have a great day.